Now I will be putting on the camera for the checking the voltage over here. Yes, it is on. Now for the no current case. Let's hope that it goes well. Up, up. There we go. We want it to go down the rail straight. Let's see the spin. 3, 2, 1, 0. Well, that's quite nice. And you can see the swing. It's pretty big. We'll wait for some time and then we will put the current on. Just note the swing will give some time. It went out well. I hope the current case it goes down equally smoothly. Last time I did not, so it was a failed test. It hit the side and that's where the experiment was a bit spoiled. But now we shall see what will happen. It should swing back more, you see, if it goes faster by the law of conservation of momentum. But what will actually happen, let's see. Now I'll give it a few more swings. As you can see, from swing to swing it doesn't change that much, so we think that it is a reasonably well balanced pendulum. But then again, if we take the number of swings and see the difference in the angles over say 10 or 20 swings, we can work out what is the difference from swing to swing in terms of angular displacement. We can easily work that out. So that's why I'm letting it go for some time, because we will find out from swing to swing how much it decreases because of the tension over there at the top where it is suspended with the rafters. Anyway, now I think we have had enough. We'll wait another few minutes, a few more swings. That I will be putting on the voltage. 23rd of August. As you see, it was through the gravity case that it went down. Now, if the current is on, it should move faster because of the induced electromagnetic field acting upon the current which is flowing through the armature as it shorts the two rails. And there is an extra force which will move it forward, so it moves faster. Whether it moves faster or not also we shall see. It should cover the same distance in a lesser time if it is moving faster. And then as it escapes, we can work out what is the velocity from the time and the distance approximately, but that will give the idea. And then we can find out in both cases whether it was moving faster or not. Well, anyway, I think now we'll start we'll take out the insulator and then we will put on this tightlet so that these two parallel bars are now well fixed. And now we know that the voltage has become 16.51 or something like that. Yes. Now we shall see what happens. And I do hope that it does not foul as it did last time today. Well, let's hoping for the best. Let's hope it moves fast and goods shoe down. It's steady now. 3, 2, 1, 0. Good, it went fast. And it hit that door. But the swing should have been, I think, a bit more, or it went so fast. But we will see from the detailed video what happened, because it was a successful experiment so far as the railgun is concerned. It moved fast. Now what happened to the recoil, that is something we have to work out from the detailed analysis. But it did move very fast, didn't it? Well, so that's the experiment completed from now. Now we shall analyze the results and then see what happens, whether there was a recoil matching the extra velocity or not. Good. 3, 2, 1, 0. Well, that's quite nice. And you can see the spin, it's pretty big. Well, anyway, I think now we'll start we'll take out the insulator and then we will put on this tight net so that these two parallel bars are now well fixed. And now we know that the voltage has become 16.51 or something like that. Yes. Now we shall see what happens. And I do hope that it does not fall as it did last time today. Well, let's hoping for the best. Let's hope it moves fast and goods shoe down. It's steady now. 3, 2, 1, 0. And it hit that door. Hello. Now we are back in the 21st century and we will be doing the analysis of this experiment which we had just done. Now we are doing that with some modern equipment. Like this is a video camera which is making a film of the projection which is on the television, and I have got with me my laptop which is containing Mr. Gates's wonderful and free Windows Movie Maker. Now I will just put a marker at the pointer to show that, well, this is the position when without the armature it is steady, and then we will see how far back it moves for both the current case and for the non-current case. Now this is the moment it starts when my hands are just leaving it, right? So let's see what happens. Over here we have got 38.36. That is the time on that scale. Now we will see what is the time it just leaves the rails, okay? And how many rotations. You see the yellow is over there at a particular angle. So that's one rotation. That's two rotations. That's three. And that's 4 when it is just about to leave it. And it leaves it at 39.30. That is the time when it actually leaves the rails. Right, and let's see what is the time when it leaves the whole system. Let's see, this is the time when it just on top of it, about just leaving, and it is 39.46. Okay then, now let us see what happens when we put on the current. Now let's start this way. Yeah, now I have left my hand off and we can see the angle of that thing also. So it is 11.74, right? Now let's see. That's one turn. That's two. Oh, sorry, let's go it backwards. I think I may have made a mistake. Let's see now. So this is where it starts. Just observe the white one, right? I mean yellow side. Yes. That's one. That's two. That's three. And I think it's about 3.5. Or a bit something like that. About 3.5 turns it has made. And let's see what yeah, so now it is leaving it at 4.6 12.60, right? And yeah, yes, and the final that's at 412.46. That is the last time, that is the last position on the rails as far as we can make out. And I think it has done about 3.5 turns or a bit something like that. So it has not really rolled faster, but it has moved slow. Now let us see what happens. The maximum swing it has gone. What is it? And then here we are taking the pointer. Okay, now we are taking the pointer. So where is the maximum? Now that goes this way. So let's see. Yeah. So I think this is the maximum it has gone with the current. Agreed? And now let us put a marker over here. Okay, so this has gone for the current case. Now we'll see what happens. This should be more than what, because it has moved faster, I think. Let's go back to the non-current case and see what's happened there. Where is it? Yes. Three, two, one, zero. Okay, now let's see how far it has gone. Think this is the maximum? Okay, let's do it. Now let's compare over here. This is very slightly about the same as what had happened earlier. And now just look very carefully at the next two video slides. You will find that the swing back of the pendulum is nearly the same no matter how fast the armature goes down the rails. Over there at a particular angle. So that's one rotation, that's two rotations, that's three, and that's four when it is just about to leave it. And it leaves it at 39.30. That's one, that's two, that's three. So we find that for the non-current case, the time the armature spent on the rails was 0.94 seconds, and for the non-current case, and for the current case it was 0.72 seconds. We get it from these values, these and this one from this and this. Immediately we see that when we put the current on, the armature moves faster because it covers the same distance, which is 528 millimeters, in a shorter duration from 0.94 seconds to 0.72 seconds. We also note that there is a 4 millisecond or so error in our measurement, which is around, since we are taking the time of around 1 second, it is about 5 or 6% error. But that we can obviously, with better experimentation, when we have a better resolution, we can reduce it. But with our simple camera, this is about what we can do, and our simple measurement systems. The time spent on the system, not on the rails, but over for the armature was 1.1 second and 0.86 seconds. Now we are finding out the way we have done before that the average current was 2440.9 amperes. This is because so many coulombs, 1757.5, they were discharged in 0.72 seconds. Now the time it spent on the system is absolutely irrespective so far as momentum calculations are concerned with respect to what happens inside the system, whether it is current is on or not. What really matters is how fast did it go back in order to calculate what should be the reaction. Now in this case, this 0.73 meters, which is the length of the run from the start to the finish when it just exits, was completed in 1.10 seconds, and this gives us an average acceleration of 1.2066 seconds for the non-current case. Similarly, 1.97 meters per second square for the current case. From there, from the formula V is equal to AT, we find out that the exit velocities are 1.327 meters per second for the non-current case and 1.697 meters per second for the current case. This is undeniable, and we also find out that the momentum, which is nothing but the exit velocity multiplied by the mass of the armature, is 3.240 kilogram meter per second for the non-current case and 4.145 kilogram meter per second for the current case. Now we have found out from the video of the swing, that the swing back was about the same, but there was a reasonable swing when for the non-current case when it went off, and also for the current case, but there should be an extra swing of 28% because it is exiting with the current case with a greater momentum. This has been a very important experiment. What we have found is that as the armature exits the system for both the current and the non-current cases, the swing back of the pendulum is about the same. And this appears to violate the law of conservation of momentum. Because I have done this experiment many times. For the non-current cases, I have filled the armature with sand and lead, and it was empty also. So I managed to get a different momentum for the armature for various cases, for these three cases. And I found that the swing back was proportional for the non-current case, I must add, for the momentum that was used to eject the system for the non-current case. But for the current case, this does not seem to hold, because as the armature goes down the rails and exits the system with greater velocity, the swing back is not proportional to the momentum that was used to eject the system, both with the gravity and with the gravity plus the current. So when the current is getting applied, an extra momentum is not being applied in the reverse direction. This is a very new finding. It is a great discovery, like fire for human use and the wheel for faster motion and efficiency of transportation. And now we find that, well, what to do with this? Why is this happening? You see, what is happening is that as the armature is rotating faster because of the extra electrical force, it should be pushing back the system back as per the normal case. Also, there is more sticking, which means that the frictional coefficient is high, and therefore it should be pushing it back. But on the other hand, the force that is accelerating it is also breaking the whales, so probably the force that is used to break the whales is compensating for the extra force, which basically means that the swing is about the same. But what happens to the reaction force? If there had been a reaction force, then no matter how fast the armature would have gone down the rails with the electricity applied on top of the gravity, the swing back would have been more and comparable to the case for the non-current, where the faster it gets out, the more back it swings. So we have to conclude from these experiments that the force that is accelerating the armature does not have a reaction component. In other words, we are getting a pure thrust without any reaction. This is a great finding, and from here we can come to the next step. All right, we may have broken Newton's third law of motion for the case where electricity is involved in huge amounts of current. But how can we put this to another test? Can we break Newton's first law of motion, that of inertia, when we trap the armature as it exits the system and makes the whole system moves forward? We shall see this in the next set of experiments.